Hello again, this is Chapter 11, Infinite Sequences and Series. We're on the topic of power series, and we just came off of finding a Maclaurin series for the function y equal to sine x. We found a Taylor representation for sine x around a equal to 0, and remember that was n equals 0 to infinity of minus 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial, right? And remember, we were using a table and calculating individual Taylor coefficients, and remember that if a function has a Taylor series expansion, then that Taylor coefficient would look like the nth derivative evaluated at a over n factorial. But we avoid saying, so here I'm looking down, we avoid saying that f of x actually equals that Taylor coefficient times x minus a to the n, since we actually need to prove that the sum of the Taylor series actually converges to that specific function on its radius of convergence. So remember what it means for a series to converge. Well, that means its sequence of partial sums converges. And so in this sentence down here in general, f of x is the sum of its Taylor series if the limit as n goes to infinity of its Taylor polynomials, and remember these are your Taylor polynomials, for example, t sub 5 of x is equal to the Taylor polynomial of degree 5. Or order 5. Good, so the fifth power is the highest term in your Taylor series expansion that you would include for your Taylor polynomial. But that would be your sequence of partial sums, is the sequence of Taylor polynomials. And so if you can show that the nth Taylor polynomial actually converges to f of x on its radius of convergence, then you can determine that f of x actually is the sum of the series. So remember, r sub n, this expression here, is known as the remainder, right? And remember, if you're going to approximate your function f of x by a Taylor polynomial, then you would have that t sub n of x plus r sub n of x would equal f of x. Good? So then, if we actually want to show that the limit of the t sub n's goes to f of x, then actually we can use this theorem here. So if f of x is the nth Taylor polynomial plus its remainder, and remember the remainder is just the tail of that series, then t sub n is the nth degree Taylor polynomial of f at a, and the limit as n goes to infinity of the remainder should go to 0. Then we can say that our function is equal to the sum of its Taylor series. So it's just a matter of showing that that remainder goes to 0. And usually we do that by making use of the Taylor inequality. So let's take a look at the Taylor inequality here and what it means. If the absolute value of the n plus first derivative of f of x is less than or equal to m, where m is an upper bound for that n plus 1th derivative, for your x minus a less than or equal to d, and usually d would be your radius of convergence is usually what you want to use d for. Then the remainder, r sub n of x of the Taylor series, satisfies the inequality that the absolute value of r sub n of x is less than or equal to that upper bound over n plus 1 factorial times x minus a to the n plus 1 for any values that satisfy x minus a less than or equal to d. So here we're going to make use, remember that we came up with the Taylor series expansion around a equal to 0 for sine x, and that was n equals 0 to infinity of minus 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. And now we do know that if we're going to be calculating the n plus first derivative of sine x, so here we have f of x equal to sine x, we know that the n plus first derivative of f of x is going to be either plus or minus sine x or plus or minus cosine x, because remember the derivative of sine x is cosine, the derivative of cosine is negative sine, the derivative of negative sine is minus cosine, and the derivative of minus cosine is minus sine, which is sine. So we alternate in our various arbitrary nth derivatives or n plus first derivatives that we're either going to get plus or minus sine x or plus or minus cosine x. And we also know that sine x varies between 1 and minus 1, and also cosine x does. So we can make that claim that the absolute value of the nth derivative of sine x is certainly going to be bigger than 0 because it's absolute value, and that's inside there is going to be plus or minus cosine or plus or minus sine, and that is obviously going to be less than or equal to 1. So we can choose here, choose m equal to 1. Good. Now it is helpful to know that we do have that e to the x equal to x to the n over n factorial, n equal to 0 to infinity, converges for all x, right? Because its interval, its radius of convergence is r equal to infinity. So that tells us that the limit as n goes to infinity of x to the n over n factorial has to go to 0 if that series is going to converge to e to the x. So that's a helpful fact to know. So now we're going to make use of the Taylor inequality. So let me just change my color. The Taylor inequality is absolute value of r of n of x less than or equal to, where we have m over n plus 1 factorial times x minus a, and a here is 0, so this would be x minus 0, which is just x, and we would have to the n plus 1, right? On for any value of absolute value of x less than or equal to d. So here, if we're using m equal to 1, we see that our remainder is less than or equal to 1 over n plus 1 factorial times absolute value of x to the n plus 1. And we see then, if we take our limit as n goes to infinity of absolute value of Rn of x plus 1, that's going to be less than or equal to the limit as n goes to infinity of absolute value of x plus n plus 1 over n plus 1 factorial. And note our useful fact up above, and regardless of n plus 1 versus n, we do know that this is going to 0. And since r sub n is clearly going to be bigger than or equal to 0 for the absolute value, then by squeeze theorem, the limit of, as n goes to infinity, of absolute value of r sub n is going to go to 0. And since that is the case, therefore we can say that sine x actually is the sum of our series minus 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial, and its radius of convergence is equal to infinity. Good. So the last couple videos that we have been, and so that is how you would demonstrate that sine x is actually the sum of that series. We have so far gone over a lot of these. We've developed our series representation of Maclaurin series for the following functions: 1 over 1 minus x, e to the x, sine x, cosine x. We've derived inverse tangent of x, and the ln of 1 plus x. You can look at various textbooks for the binomial expansion. But now we're going to be introducing some applications of these series, and also still continuing with how can I find Maclaurin series or Taylor series expansions for other functions. All right, so that looks like I've been doing some stuff in here, so let me just erase these things, or we can discuss them. Representing real numbers with Maclaurin series. We can represent real numbers as an infinite sum and approximate these values using the Taylor series, in addition to using known Taylor series to find sums of various things. So if I'm looking at evaluate the sums of the following series, looking at the known series above, I can see that minus 1 would be equal to my x, right? And if this is my x, we can see that that's e to the minus 1. So I can approximate e to the minus 1 with, and if n is equal to 0, I've got 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial. And then I can use a calculator to approximate that value. And the more terms that we use, the more accurate our assessment is. And a lot of computer programmers will do this to do the programming for your scientific calculators. And that's how they would pretty much calculate e to the first power or e to the second power. Again, we have that here. We're looking at, I see a 2n factorial in the denominator. I also see a minus 1 to the n with this series. And so I kind of want to play with that 2 to the n and use my exponent rules. And I see here that my x to the 2n in here, so this is not quite right. I see partial, right? And I'm going to see that this here, x equal to pi over 4. And so this is roughly going to equal cosine of pi over 4, because I know that cosine x is equal to n equals 0 to infinity of minus 1 to the n over 2n factorial times x to the 2n. Right? And if I see in here that my x is pi over 4, then I know that this is going to be cosine of pi over 4. And so I can say that this is equal to square root 2 over 2. Good. And here, I want to break that out. Sorry about that. All right. So that's kind of fun to do. And use a Maclaurin series for sine x to compute sine of 5 degrees correct to 8 decimal places. So how would we do something like this? And this is what your calculator would be doing. First off, keep in mind that when we are calculating outputs for sine and cosine as functions of x, x is a real number, so we do want to convert our 5 degrees to be in radian measure. So with x equal to 5 degrees, convert to radian measure first. And so we would say 5 degrees times, there are 180 degrees, 2 pi radians, and so we would have 5 pi over 180. And how much is that? We have 20 plus, what is it, 180 divided by 5, or we have that this goes to 36. So this is going to be pi over 36. All right. So we want to calculate sine of x using our power series representation. We have minus 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. So sine of pi over 36 is going to be n equals 0 to infinity of minus 1 to the n over 2n plus 1 factorial times pi over 36 to the 2n plus 1. Right, so whatever we calculate in here, we want to calculate in here. So if we just write out the first couple of terms here for n equal to 0, we start with a positive value, and we have that this would be 1 over 1 factorial times, for n equal to 0, pi over 36. When n is equal to 1, we subtract, and we have 1 over 3 factorial times pi over 36 to the third power, and we'd have plus 1 over 5 factorial times pi over 36 to the fifth power, minus 1 over 7 factorial times pi over 36 to the 7, plus dot dot dot. And we could begin with our calculator and begin calculating with decimal places here. Find decimals for each term. Right? And note here that we have an alternating series. And because we have a convergent alternating series, our estimate, our remainder, our error, r sub n, is going to be no more than the very next term that we leave off of our estimate. So what we would want to do is find which term, like we'd want to say maybe the seventh term here, is this term less than or equal to, and it said to calculate correct to 8 decimal places, so maybe we want to say, is this term less than or equal to 10 to the minus 9, which is 9 decimal places. And if so, then we can just use this first couple of terms as our estimate. That would be correct to 8 decimal places. So you get the idea of how we can use a series expansion to estimate the output for a function and be pretty satisfied with how accurate we are. All right, so I'm going to stop here and create a separate video to go over some other applications or how to